Next up is Sorel Muresan from AstraZeneca. Sorel is a chemist by background, been working in cheminformatics and informatics for about 10 years or so, he says. His function at AstraZeneca is to lead our cheminformatics group there, and he's going to continue the story on naming.
Yeah, thank you, Tim. We will stay in the same area of chemical text mining. We had two great talks describing various challenges on chemical text mining and on name constructors, on chemical name entity recognition. And I'll try to describe our attempts at improving the text mining process, a chemical text mining process through automated spelling correction. I should also say that this was a collaboration with Nextmove Software. Roger Sell, who is here in the audience, helped us with developing some of the tools that I will be presenting. The motivation for us doing this work and this study was twofold. Firstly, is the ever-increasing volume of SAR data. Generating in vitro SAR data for compounds modulating protein target is the defining paradigm in the research phase of the drug discovery. And the single largest published source of in vitro SAR is patent applications. You see here a graph showing the number of patents published for the last decade, according to the European Patent Office. And I think the shape of this curve is interesting in itself, but what I wanted to say is that considering an average of 50 compounds per patent and perhaps 5 patents for each patent family, we are talking about close to 400,000 structures published each year. So a lot of chemistry that we need to access and search. A lot of new chemistry, because especially in the industry, novel chemistry is first published in patents and only later, if at all, appears in scientific journals. And this is the rule rather than the exception. You see an example here of a set of compounds described in a scientific journal in JMed Chem in 2006, and the same data practically being published 2 years earlier in a patent. And we also have to account for the 18 months between the filing and the application. So again, patents are very important, a very important source of novel chemistry in our area. The second driver, and this was already mentioned a few times already, is the error rate that comes from the OCR process. So we were trying to see if we can improve the chemical named entity recognition process through automated spelling correction. A few examples of such errors, and while a chemist could probably easily spot these errors, correcting this automatically poses some challenges. Another nice example that I took from Wolfgang Thielmann, from an example that he presented at an IRF symposium a couple of years or a few years back, is looking at a chemical term, simvastatin, a drug name, and searching a large patent corpus with this term, brings back just over 9,000 patents. However, there is still a large number of patents that cannot be found because of various typos, misspells, and OCR errors. And this is quite informative, I thought, because you can see the type of errors that you can find. You can easily spot OCR errors like S1 and vastatin, or typos. And sometimes, actually correcting such a name is a challenge, because in this case, if you look at simvastatin, this can be simvastatin, but can be rivastatin as well, which is another chemical, it's another drug. So and you can also see the number of edits, the number of corrections you would need to make to correct these names. Just to give the context of this work, in 2009 we started at AstraZeneca a project called Chemistry Connect, where we've tried to bring together into one place many SAR databases, small molecule databases that we have access to, internal and external data sources, but also chemistry and SAR data coming from patents and journals. And the reason for doing that was to be able to have one port of call for chemistry queries. We are using actually different pipelines to extract chemistry and annotations from patents, and we do that through manual curation, expert extraction by licensing data sources, and in this case from GVK Bio. And 2 years ago when I was here, I presented some details on this system we built, and we also extract chemistries through text mining via collaboration we have with IBM Almaden. Now the reason we are using different approaches is the volume of the data that has to be handled and the quality of the data. GVK Bio database is a high quality data but a low volume, so we have about 50,000 patents coming through this system, while via text mining, as we've already seen, we want to be able to process millions of patents, perhaps with a lower quality or lower output. Everything goes together into one place using, a unique set of chemistry rules, similar to the ones that were just described this morning, and then the data is consumed by internal application via web services. So really, this work is part of this text mining process we are developing with IBM and XMove software. The text mining pipeline is usually includes, and requires access to the full text patent, either as full text or various formats, XML. The words are split and then they are recognized as chemical entities through a variety of algorithms using, dictionary-based matching or a more sophisticated NLP, natural language processing algorithm. The output is then fed through to a name-to-structure converter, and we've seen a few results already, and they are translated from text to connection tables that eventually are registered into a relational database, for queries. All these processes have challenges, starting with the errors we encounter, all the way at the beginning through the OCR process. Then the typos and the OCR failures that are then passed through the chemical entity recognition process. We've seen that different name-to-structure software have strengths and weaknesses, and then all the way to registering these compounds in a database, making sure there is a proper chemical registration system in place, and also a system that can handle large number of structures. And this work really focuses on this middle part, trying to look at the chemical named entity recognition process, trying to fix typos and then feed that back through the name-to-structure software. And for that, we started a collaboration with NextMove software, and Roger developed a tool called CaffeineFix that is addressing this issue of spelling correction. And this is supposed to be a pre-processing step in the text mining pipeline, working just before the name-to-structure converter, and because of that, it can actually work with any name-to-structure software. And we'll see some results. To see how ChemAxon works, I'm coming closer to you, Roger, now. Let's consider a small lexicon of 4 arcanes, and in essence, a chemical named entity recognition is a text matching, is a string matching of terms of keywords describing chemical entities. We can do that by having dictionaries, large list of chemical entities, and matching every word. That's not that efficient because the matching process depends on the size of the dictionary. The performance decreases with the size of the dictionaries, and these dictionaries are difficult to maintain. But because such dictionaries are known a priori, we know we have the list, and sometimes we can actually describe or define them through grammars. Such lists can be pre-processed to allow for a more efficient string matching. And this is the way caffeine works, using what's called finite state machines to do the string matching. To allow for more efficient text matching, the list, the dictionaries or the grammars are translated into graph-like representation. And the simplest of such a graph-like representation is a tree. And so this is an example of a tree for the 4 alkanes that I just presented. It starts with a root node, which is always an empty string. Each internal node is a prefix, and each leaf is a full word. The nodes are connected through edges, each branch being labeled by one single character, and each node has, for a tree, each node has one incoming edge and can have one or many outgoing branches. Now the matching process is quite simple. We start at the root node. We look at the first character in the word we want to match. If the character is any of this, in this case 4 branches, then we advance to the second state and so on. So for instance, if it's the first character is a E, we advance to this state labeled here too. Then we go to the second character. If that's not T, it means we already know that word is not in the dictionary, and then we report the failure. If that second character is a T, then perhaps we can traverse the whole finite state machine, and at the end of the word, if we are in one of these accepting states, a leaf node, then we report a match. So it's quite simple, conceptually, that implementing this as in an algorithm, in the software is a bit more complicated, and Roger had to do his magic to make this extremely efficient. We can actually compress such a tree in what's called a directed acyclic graph by compressing the common branches. So you see, the matching process is identical to what I presented, but there is a more efficient way of storing such a graph for string matches. Now, we can actually, instead of having a list of terms, we can have a dictionary. And this is, imagine that we now want, next to those alkanes, recognize also their halogenated derivatives. So we need to account for locants, substituents like bromochlorofluoro and so on, parent, and then we define a grammar. And this grammar should account, for instance, and will account for such terms. And even more sort of exotic forms of these compounds. And again, it can be translated in a finite state machine that can be then traversed for string matches. Yeah. Extremely efficient because string matches using FSM, it does not depend on the size of the dictionary, and they are as effective with millions of terms as with just a few. So for instance, you start with 1, you'd have to have a dash, and then, bromo, propane, for instance. I'll come back to this example because you see that this particular representation of that simple grammar actually require a dash after the locant. If that's not in there, then the term is not recognized. Using the same procedure or the same algorithm, we can now encode other dictionaries of grammars. For instance, something very useful in the in the pharma industry, the registry numbers or development codes. which usually have this form, like for AstraZeneca, we have AZ, we call AZ numbers that are, coming through the registration process, AZ and a number, or AZD and a number for our development compounds. So rather than actually storing a long list, you just store, a dictionary. And the same, for instance, for CAS numbers. Sorry for that. So the same for CAS numbers, where it's a rather simple finite state machine can, represent and encode the entire, CAS numbers. Representing UPAC names as finite state machine has the challenge of dealing with brackets, brackets, parentheses, and so on. Because every time when we open a bracket, we need to make sure, it's closed when we do the matches. And to do this effective, a finite state machine can be coupled with what's called a pushdown automata, which is an additional stack next to the FSM. So every time when we open a parenthesis or a bracket, we add that in the stack. Every time when we close one, we look in the stack if the first one is similar, and we take it out. So at the end of the matching process, we also look at the stack to be empty to report back a match. So this was an additional challenge that had to be taken care of. What is interesting is that with a relatively simple extension, we can use pretty much the same algorithm, the same match algorithm to do spelling correction. And we do that by considering various substitution, insertions or deletion at each point of the matching process. And this is an example that I wanted to give. So for instance, if we encounter in a text 2-bromopropane written like that, this would not be recognized by the finite state machine that we just presented. However, we know that after a locant we need to have a dash, so we can allow for an insertion of such a dash, and then if possible we can traverse the entire FSM and report back a match. So this is the the principle of using CaffeineFix for automated spelling correction. The number of characters that can be changed is an input parameter, and the computing cost grows with the number of changes we make. So we actually managed to run. You'll see later this process only with one character change, and there was took a couple of weeks actually to go through the entire pattern corpus that we've analyzed. So to present a few results, and it was quite nice to see the results from SureChem, because many of the data that I've seen are very similar to what we are going to report here. So what we did is analyzed about 11 million full text patterns using two text mining pipelines, one from IBM, which is using a natural language processing algorithm to extract chemical entities and Cambridge soft name to structure to generate the structures from the names, and then CaffeineFix without correction and with correction, allowing only for one character change per name, and then passing those corrected names through three name to structure software. Two, you see OPSIN here. We've used it as well. We are actually new to ChemAxon's name to structure. We just started working with it really at the beginning of this year, and we are more familiar with Lexichem since we have it for some time. So I anonymized the results, I'm afraid. But this is the first data we looked at. So the number of unique chemical names that can be extracted through those 11 million patterns by the different chemical text mining pipeline. So each row would be a different chemical text mining pipeline. You know, they all extract about 10 million chemical names, and the rate of conversion is different from you know, for different name to structure software, which we've already seen. So from, you know, 40 and some percentage to probably 25. What is interesting is that with CaffeineFix we can actually classify the chemical entities, you know, in several types, you know, because of the way we store the dictionaries and the grammars. And this is the breakdown of the chemical entities we've extracted from patents, you know, by these classes. See that the largest number of compounds in patents are actually UPAC-like structures, followed by you know, what we call fragments, you know, chloro, bromo, and like that. And then we have registry numbers, dictionary terms, and so on. So in total, about 10 million you know, unique chemical entities extracted by CaffeineFix. And if we look at the different rates of conversion for the different you know, name-to-structure software for each of these classes, we can actually see, you know, perhaps and understand why they are different, because they have different strengths. So for instance, the first one is actually better at handling UPAC-like structure, while the second one has a better dictionary, you know, and does a better translation for dictionary-like chemicals. There are some which we actually couldn't translate with none of them. And I guess this is probably you know, an area where all such all the name to structure software can improve. And because all this, I mean, ChemAxon is here in you know, in this table. But there was an older version that we looked at, so we were curious to see how you know, the 5.5 performs. And for instance, out of these 27,000 dictionary names, ChemAxon converts about 60%, which is a very good result. And I've also understood, you know, you'll tell me if I'm right, that it is possible to convert CAS numbers through the name to structure by calling a service at NCI. So this is, yeah, I think it's a great addition, and it's slow though, not because of the name to structure, but because of the web service NCI has. Anyway, I've asked Markus Sittman, who is the developer of the chemical identifier resolver at NCI, and you know, 48% of you know, the CAS numbers can be actually translated, you know, into a structure. So again, that's a great addition. Yeah. Not all the chemistry that we extract from patent and convert into structure are uploaded into that system that I've presented. And you know, we focused first on drug-like compounds, you know. So that means there is a filtering process, you know, after the name to structure conversion. And this, you see the number of, let's call them drug-like molecules that are translated, you know, or generated by each name to structure software. And it's interesting to know that, you know, the numbers are quite close to each other. However, and we've seen you know, similar results. If you look at the heat map between the different name to structure software, you know, there is well, close between 70 and 80% overlap when compared to by two. So there is a lot of chemistry that's been extracted by only one software. Perhaps even more interesting, if we look at the Venn diagram, in this case, chemical entities extracted by CaffeineFix without correction, and look at the different overlaps between the three name-to-structure software that we look at. You can see that that there is actually a large number of chemistry, a large number of compounds that's been extracted only by one software. And again, it was nice to actually see that the figures are very similar. Actually, it was about 500,000 that you've mentioned, being extracted by one. So if we run the same analysis at with correction, so allowing for error checking, with one single character, you see that the number of chemical terms that been extracted increased significantly. And again, good to see is, was that every single software, name to structure software, benefit from that correction. So this is really great news, because it means that now we can actually improve the link between CaffeineFix and in this case, the three software that we've used for converting the names. Finally, this is one last statistics that I wanted to share with you. You see that, what I want to say here is that the pipeline that IBM has at Almaden is using one single name to structure software from Cambridge, name equals struct. So just adding more such tools, improves significantly the output. And again, we've seen similar results from Nico and Andrew. Just to emphasize again, the automated spelling correction, generates or adds an additional number of chemical entities, all the way through the output. So a few, take-home messages. When we uploaded this chemistry extracted from patents into our internal system, Chemistry Connect, we realized that there is a large number of unique chemistry coming only from this process. So, using text mining on full text patent is adding a lot of information, on top of what we already have. So about 10%, 12% out of the system includes already 47 million unique parent structures. We've shown that CaffeineFix significantly improves the extraction rates. For this analysis, 22%, going from not corrected to corrected chemical entities for the filtered set. And again, a message that's been presented already. The different name to structure software, work well together. They are complementary. And it was nice to see that, actually this 40% was again presented as, as the contribution coming from any, single name to structure software. Yeah. So for us, these are all good news. There are a lot of chemistry, coming from using chemical text mining on full text patterns, and all these different pipelines and different software can, be integrated to actually improve the extraction rates. A few acknowledgements, some colleagues at AstraZeneca who helped with this work, and Marcus from NIH for helping with translating the CAS structures, and Daniel who is the developer of OPSIN. He helped us to actually running the tool, and Daniel Bonio for again helping us with understanding the name to structure converter from ChemAxon.
Okay, thank you, Sorel. We've got time for a few quick questions.
You mentioned in the beginning the extraction from SIR content from patents. You focused on the names, get the correct name out and the structure. What about the activities? Did you do some work on the activities?
We are actively pursuing that, and we've worked on, we are most advanced on extracting chemistry, chemical entities. We are doing work on extracting protein targets or targets from patents, and probably down the road tables, reactions and so on. That's more challenging. We thought this is the easiest part, so we start with this.
Do you know how safe it is to open Pandora's box and let the software play around even with one character? I mean, you have acetyl and then you have the cetyl radical, the hydrocarbon. So funny things may happen. Did you see any?
It is true. Well, I have not presented, although the slides are available, for you to look at. We've looked at precision and recall rates on a controlled set of patents, patents that are covering marketed drugs. And, we've seen what you've just mentioned, but all in all, we had a very good recall rate for that particular system. Yeah. And I also gave already a system where, an example where you simply don't know, how to correct that. Yeah.
You use CaffeineFix for OCR error fixing. Have you considered also using several tools parallel for OCR error fixing?
We've started some discussions with Daniel, trying to use your document to structure tool, which we haven't used yet, and we'll see how that complements this pipelines that I've presented. You've seen it is a difficult problem, so I think the more ways to look at the problem, more ways to solve it will probably just improve the output.
Chizzy, in fairness to Roger Sale, I should say we also use CaffeineFix, and we use about 6 other, between name fragmentation, our own heuristics. We're thinking of using the name structure as well. I think the only way you get there is you combine as many tools. That's why I'm glad we don't sell software anymore. We're technology agnostic. Sorry.
Okay, so thank you. So.
Yeah, thank you.